Example 3 says, by cutting away identical squares from each corner of a rectangular piece of cardboard and folding up the resulting flaps, the cardboard may be turned into an open box. If the cardboard is 16 inches long and 10 inches wide, find the dimensions of the box that will yield the maximum volume. So, like many of these problems, we want to start off by drawing a picture, and this is going to be 16 inches long, and this is going to be 10 inches long. And we are wanting to cut away identical squares out of each of the corners. I think my drawing's not the best, but pretend those squares are all the same size. Then if we cut out those squares, we have a shape that's left over like this. So the leftover shape is this like yellow colored shape here, and that represents the cardboard that we have left. And then if we folded all those sides up, then we'd have an open box, and it would look something like that. And although this whole length of the original piece of cardboard is 10 inches, we want to figure out what this length is here. And so in order to do that, we need to assign a variable to the square. So this is an x by x square. And so if the whole thing is 10, then the length here would be 10 minus x, which is the same thing as 10 minus 2x. And similarly, the length here is going to be 16 minus 2x for whatever that x value ends up being. So we could say that this length here is 10 minus 2x. This here is, the width can be 16 minus 2x. And then the height is going to be x there. Now, hopefully you remember that the volume of a rectangular prism is the length times width times height, and that's the thing that we're trying to maximize. We want to maximize the volume. So I'm going to write a volume formula. It's length times width times height, and we know those values in terms of x. So the length is 10 minus 2x, and the width is 16 minus 2x, and then the height is, oops, I wrote h, but I meant to write x. And let's go ahead, and if you expand that and multiply that out, you should get that the volume of the box is equal to 160x minus 52x squared plus 4x cubed. All right, so from here, we're going to take the first derivative of the volume function and then find our critical values. So we have 160 minus 104x plus 12x squared, and we're going to set that equal to 0 to solve for our critical values. And I will leave it up to you to solve that using whatever method you'd like, but I used the quadratic formula, and I got that x was equal to 2 and x was equal to 20 over 3. So now what I'm going to do is I'm going to use the second derivative test to figure out whether those are going to give us maximums or minimums. And in order to do that, I need to find the second derivative, and that's going to be negative 104 plus 24x. So let's evaluate v double prime of 2, and that's going to be negative 104 plus 24 times 2, which that will result in a negative number, and then v double prime of 20 over 3 is equal to negative 104 plus 24 times 20 over 3, which is negative 104. 24 divided by 3 is 8, and 8 times 20 is 160. So that's going to be a positive number. And I don't know why, but I always have to draw the picture. So this is concave down, so that's going to be a maximum, and this is concave up, so that's going to be a minimum. So out of the two answers, the x value that's going to give us the largest volume for our box is if x equals 2 inches. And it looks like we are wanting all of the dimensions of the box. And so we had 10 minus, or we had x as one of the dimensions, 10 minus 2x, and 16 minus 2x. So if x equals 2, then 10 minus 2 times 2, that's going to be 6, and then this will be 12. So the dimensions that give the greatest volume are 2 inches by 6 inches by 12 inches.